Hello everyone, and welcome to today's broadcast. Today's date is April 1st, 2026, and it is a lovely Wednesday. I'm Sam though, your friendly neighborhood radio host, and I'm super excited to be here with you all today. Today I'm introducing a really fascinating and trending article from the archive, and I just know you're going to find it as interesting as I do. The title is Interpretable Ensemble Learning from Network Traffic Anomaly Detection, a SHAP-based Explainable AI framework for embedded systems security. It is long, but do not worry, because I am going to break it all down for you in a super fun and easy to understand way. So, what is the big problem that this paper is trying to solve? You might ask. Well, in a modern world, we've tiny computed into almost everything, which we call embedded systems. These are the brains inside your smart home devices, industrial machines, and even critical infrastructure like power plants. But because these devices are constantly connected to the internet, they face a huge number of cyber threats every single day. Bad guys are always trying to hack into them to steal data or mess up how things work. Now, traditionally, people use something called signature-based detection to catch these hackers. Think of it like a security guard holding a wanted poster. If the security guard sees a face that matches the poster perfectly, they stop the person. But if the hacker wears a brand new disguise, which is called a zero-day attack in the tech world, the traditional security guard has no idea who they are, and just lets them walk right through the front door. To fix this, smart people started using artificial intelligence and machine learning to catch hackers. Instead of looking for a specific wanted poster, AI learns what normal behavior looks like and flags anything that acts weird. But here's the catch. Most advanced AI models are like big, mysterious black boxes. They might say, "Hey, this network traffic looks malicious." But when the human engineers ask why, the AI cannot explain its reasoning at all. This lack of trust is a huge problem for critical systems, because engineers need to know exactly why an alarm is going off before they shut down a factory or a power grid. That is exactly where this amazing paper steps in. The researchers decided to combine two powerful concepts, which are ensemble learning and explainable artificial intelligence. Ensemble learning is basically teamwork for AI. Instead of relying on just one AI brain, they use a whole team of them, like random forest and gradient boosting models. They tested a bunch of different models and found that the random forest model performed the best, achieving a really impressive 90% accuracy on the validation data. But the researchers did not stop at just making a highly accurate model. They wanted to open up that black box so humans could look inside. To do this, they used a technique called SHAP, which stands for Shapley Additive Explanations. SHAP is basically a translator that turns the complicated math of the AI into human understandable insights. It tells us exactly which pieces of information the AI used to make its decision. For example, the SHAP analysis revealed that the top 3 most important clues for detecting a hacker with a packet count over 5 seconds, the inter-arrival time between data packets, and something really cool called spectral entropy. This paper is actually super unique because it uses frequency domain features. Instead of just looking at the timing of data, they used a mathematical trick called the wavelet transform to look at the energy and frequency of the network traffic. This helps catch sneaky hackers who try to hide their attacks in repetitive or encrypted patterns. Compared to older technologies, this approach is incredibly groundbreaking. Traditional signature methods are completely blind to new attacks, while standard machine learning models are too secretive to be fully trusted. By pairing highly accurate ensemble learning with SHAP-based transparency, this framework gives us the best of both worlds. It catches the new sneaky hackers, and it clearly points a finger at exactly what gave them away, making it safe to use in sensitive embedded systems. Now, let us talk about how this applies to our everyday lives. have 3 specific application examples to share with you. And they're all super cool. First, let us think about smart home devices. Nowadays, many people have smart cameras, smart locks, and smart thermostats in their houses. If a hacker tries to break into your smart camera to spy on you, they might send a rapid burst of data packets to overwhelm the system. Using the technology from this paper, the AI embedded in your home would instantly notice because the AI is interpretable. It would send a clear alert to your phone saying, "Hey, someone is sending too many requests to your camera," allowing the system to automatically block the attacker before they can invade your privacy. Second, this technology could totally revolutionize industrial control systems. Imagine a huge factory that manufactures cars or processes food. The machines in this factory talk to each other using embedded systems. If a bad actor tries to sabotage the factory by slowly altering the commands sent to a robotic arm, a traditional security system might miss it. But the Ensemble AI from this paper would detect the subtle changes in the inter-arrival time of the network messages. The SHAP explanation would show the factory engineers exactly which robotic arm is receiving the weird data, allowing them to pause that specific machine for maintenance without having to shut down the entire factory, saving millions of dollars. Third, we can apply this to smart city infrastructure and power grids. Keeping electricity flowing safely to hospitals and homes is literally a matter of life and death. Cybercriminals often try to launch complex, encrypted attacks against power grid sensors. By utilizing the spectral entropy and frequency band energy features discussed in this paper, the city's security system can detect these hidden rhythmic attack patterns. The explainable AI would provide the deburst team with the deal breakdown, showing that the abnormal frequency energy is coming from a specific neighborhood substation. This allows the city to isolate the compromised substation and reroute power seamlessly, preventing a massive blackout. It is just so amazing to see how artificial intelligence is evolving. We're moving away from blindly trusting computers and moving toward a future where computers can actually explain their thought process to us. This makes our smart devices, our factories, and our cities so much safer and more reliable. Well, that is all the time we have for today's deep dive. I hope you enjoyed learning about Ensemble Learning and Explainable AI as much as I did. Thank you so much for tuning into my radio show today. I am saying no, wishing you a safe, happy, and wonderful Wednesday. Catch you next time.